Let's talk about analyzing RC series circuits using differential equations. Suppose we have a simple electric circuit with a voltage source, a resistor, and a capacitor. The capacitor stores energy by building up an electric field. Suppose the voltage at the voltage source is epsilon volts, the resistance is R ohms, the capacitance is C farads, and the charge at the capacitor at time t is Q of t coulombs. Then dq dt equals epsilon C minus Q over RC. This is what enables us to find a formula for Q. Okay? For example, a 100 volt electromotive force, EMF, is applied to an RC series circuit with a resistance of 400 ohms and a capacitance of 10 to the negative 4 farad. Find the charge Q of t on the capacitor if Q of 0 equals 0. So again, we start with the differential equation. dq dt equals epsilon C minus Q over RC. Just plug in everything we know. Epsilon, that's the voltage, that's 100. The capacitance is 10 to the negative 4. Q we don't know, so we just leave that alone. The resistance is 400 ohms. And again, the capacitance, 10 to the negative 4 farad. When you multiply all of that out, you end up with 0.01 minus Q over 0.04. Now, this is a separable differential equation. So let's separate it. We're going to get the Q's on the left side. We have dq over 0.01 minus Q equals 1 divided by 0.04 dt. That's if we get the dt on the other side. 1 divided by 0.04 is 25, so we'll just write that as 25 dt. Okay, before we integrate this, I don't want something minus Q because then you have to use substitution to integrate. It just gets complicated. Let's just multiply both sides by negative 1. We have dq over Q minus 0.01 equals negative 25 dt. Okay, there's our equation. Let's integrate. When we integrate this, we end up with the natural log of the absolute value of Q minus 1 equals negative 25t plus C. When we get rid of the negative sign, or when we get rid of the absolute value signs, we end up with natural log of Q minus 0.01 equals negative 25t plus C. You know what to do. We raise e to both sides so we can isolate the Q. E to the natural log Q minus 0.01 is e to the negative 25t plus C. We can break that up using the law of exponents as e to the negative 25t times e to the c. Okay, so e to the c is just a constant. So we're just going to call that constant c. Okay, so e to the natural log q minus 0.01, that's just going to be q minus 0.01. So we have q minus 0.01 equals c e to the negative 25t. Add 0.01 to both sides, and we get q equals 0.01 plus c e to the negative 25t. Okay, so that's our formula for Q, in other words, Q of t, the charge at time t. To find C, let's plug in t equals 0. So Q of 0 equals 0.01 plus C e to the negative 25 times 0, which is 0.01 plus C e to the 0. E to the 0 is just 1, so this just simplifies dramatically to 0.01 plus C. And Q of 0 we know is 0. We were told that. So we have 0 equals 0.01 plus C. That means when we move the 0.01 to the other side, that negative 0.01 equals C. So here's our formula for Q of t, the charge at time t. It's 0.01 minus 0.01 e to the negative 25t, because C is negative 0.01. Okay, find the current I of t. It turns out that the current I of t is the derivative of the charge, dq dt. So let's take the derivative of Q. Q, remember, was 0.01 minus 0.01 e to the negative 25t. When we take the derivative of that, here's what we get. The derivative of 0.01, that's just going to be 0. And the derivative of this hairy expression, okay, recall that when you take the derivative of e to the negative 25t, you're going to e the negative 25t, and the negative 25 is going to pop out front. So the derivative of what I've just circled is negative 25 times negative 0.01 e to the negative 25t, which simplifies to 0.25 e to the negative 25t. That is our formula for the current.